All right, good morning, everybody. So last class before the break. So tonight, homework 6 is due. It's reading week next week. So obviously no classes, no labs, no tutorials. Also, we won't have obviously a homework due on Friday during the reading break. So you have the homework due tonight, then the next one will be due 2 weeks from today. Okay. When we come back from the break, we'll do lab 4, and there will be a pre-lab 4. So we'll get that posted at some point during the break. And so if you want to get that done early, you'll have that opportunity, I think. And then just a final reminder, well, maybe not a final reminder, but a reminder that we will have our midterm in person in class on Wednesday after the break. So that's February 28th. So it'll be here during regular class time. It'll be a paper midterm. And then there will be no tutorials the week of the midterm. So when we have the reading week next week, and then the week after that, there'll also be no tutorials. Okay, good. So what we were talking about the last, I don't know, class and a half or so was capacitors, and specifically these parallel plate capacitors. So we imagine two plates of some area A, they're parallel to one another and they're separated by a distance d. We place a positive charge on one of the plates and then an equal but opposite negative charge on the other plate. We could do that, for example, using a battery. And so what we were able to work out is that the definition, well, we didn't work anything out. We just defined capacitance to be Q divided by delta V. And so it's how much charge can we store on a capacitor per unit volt across the plates. And we went through a bit of an analysis and we worked out that for the parallel plate capacitor, the capacitance could also be determined just by some geometrical factors. Okay, and then we kind of wrote down some schematic circuit symbols for our components, which makes it easier to draw symbolically the sorts of circuits that we might be interested in analyzing. And the capacitor circuit symbol was just very simple, 2 parallel lines. The circuit symbol for a battery was also 2 parallel lines, just one was shorter than the other. The shorter line represents the negative terminal of the battery, and the larger line represents the positive terminal. Okay, so we did a problem last time where we imagined we connected a parallel plate capacitor to a battery. And so the battery provides some voltage, and we calculated, or we could calculate how much charge is stored on the plates. So then we said, okay, what if we left the battery connected, but then pulled the plates apart a little bit? So I think what we did is we tripled the distance between the plates, and we wanted to calculate what happens to the charge. Well, what we discovered is that the charge on the plates goes down by a factor of 3. And the idea was that the capacitor is used to store charge, and the amount of charge that it can store is proportional to the capacitance. And when we pull the plates further apart, we reduce the capacitance because C was equal to a constant epsilon naught times A over D. So if we increase D, C goes down and we store less charge. So what I want to do today is I want to start by kind of thinking about a similar problem with like a little change. So this time we're going to take our capacitor, we're going to connect it to a battery, and we'll store some charge on these plates. Then what we're going to do is we're going to disconnect the battery first, and then pull the plates apart. And I want to see what happens in that case. So that's different, right? In the first problem, the battery was connected. We pulled the plates apart. In that problem, the voltage across the plates can't change because the battery is always connected. In this version of the problem, we're going to disconnect the battery after the plates are charged up, and then we're going to pull them apart, and I want to see what happens. Okay, specifically, we're going to ask what happens to the charge on the plates, and then what happens to the potential difference between the plates. So let's just remind ourselves, we'll just draw the common picture that we draw. So our circuit is a battery with a positive and a negative terminal. We put some positive charge on, say, the right plate, and sorry, that's the left plate, and we put some negative charge on the right plate. This is our capacitor C. Okay. And let's suppose that this is the initial situation where what we have is a distance d between our plates. So if we wanted to, say, calculate the charge, well, let's see, C is Q over delta V, and let's say that our battery is providing voltage delta V. Then Q is C delta V. But we know how to calculate C. That's a constant epsilon naught times the area of the plates divided by the distance times delta V. So that's initially what we have. Maybe what we could do is we can call this Q. Now, but now what we're All right, thank you. So I'm not muted anymore. I guess when Zoom restarted, it automatically muted me, I think. Okay, so in the first problem, when we pull the plates apart, some of the positive charge from the left plate travels through the battery towards the negative plate. And so that positive and negative charge cancel each other out partially, and we get a reduced charge on the plates. In this problem we're doing now, when the battery is not connected and we pull the plates apart, there is no circuit, there's no path for the charge to go anywhere. And so the charge must stay fixed. So since there is no closed circuit, the charge cannot flow, and so therefore Q remains constant. Okay, so specifically Q1 is going to be equal to Q2, and so if we call this Q2 and this is Q2 as well with a minus sign. All right, so that's the first little bit of insight. What a battery does is it keeps the voltage constant. When there is no closed circuit, the charge has to remain constant. Let's see if we can get this into. I can't. Okay, that's okay. All right, so that's part A. Then in part B, what we're asked is to calculate the voltage. Okay, so let's see. C is Q over delta V. That's the definition of capacitance. So that means delta V, absolute value, let's say, is Q over C. And so all we have to do now is think about the initial and final cases. So let's do the initial case over here. Q1 is just equal to Q, let's say. The charge is never going to change, so we'll just call it Q. We don't need a subscript. All right, so delta V1 is going to be equal to Q divided by C1. So C1 is the capacitance before we separate the plates further apart. But C1 is epsilon naught A divided by the distance between the plates. And so initially, the plates are separated by a distance D. And so if we simplify this, we could say, let's see, that's Q times D over epsilon naught A. All right. So final, everything's exactly the same, except for one little thing. Q2 is just going to be Q. Charge is always the same. And delta V2 is going to be Q over C2. And C2 is epsilon naught A. And here's the only difference. The only difference is now the plates are 3 times further apart. And so the distance between them is 3 times D. So what we end up with is delta V2 is equal to 3QD over epsilon naught A but this QD epsilon naught, QD divided by epsilon naught A, that's just delta V1. Okay, and so that means, therefore, the difference in voltage across our capacitors after we pull the plates apart with the battery disconnected is 3 times delta V1. So that's one way to think of it. There's another way to think about this problem, and that is if we know the charge is not going to change, the electric field between our parallel plates is going to be the charge per unit area sigma divided by epsilon naught. Okay, and so let's think about this alternative approach. Alternative approach. It's nice to try to solve these problems in multiple ways. And it's often possible to do that relatively easily. So if Q is constant, then we know that the electric field between the plates is given by, let's see, it was E was equal to sigma over epsilon naught, but sigma is just the charge per unit area. Okay, so let's just draw a picture of that. So here's our positive plate, here's our negative plate, and then we have an electric field that points from positive to negative. And so here's our electric field is sigma over epsilon naught. So if Q stays constant, then when we separate the plates, nothing happens to the electric field. So therefore, in this problem, E remains constant. When the plates are pulled apart. All right. Another thing that we had worked out previously is that the difference in voltage as you move through a constant electric field is equal to E times however far you move. So recall that the way we calculate voltage differences was this integral of from position 1 to 2 of E dot, say, dl. There was a negative sign, but if I'm interested in just, I've wrote down just the absolute value of this voltage difference, so I'm not worried about the sign. Now, here what we have is we're going to move from, let's say, position 1 at our positive plate to position 2 at our negative plate in a straight line parallel to the electric field. The electric field's constant, and so for our parallel plate capacitor, parallel plate capacitor, this E dot dl is just going to be equal to E times L. So for our initial situation, L, the distance we move is just the separation between the plates. It's just D. And so therefore, delta V1, let's say absolute value, is just E times D. And for the final situation, our plates are 3 times further apart, so the distance we have to travel from positive to negative plate is 3 times larger, and so that means delta V2 is equal to 3 E times D, which is 3 times delta V1. And so that's the same result that we got using the first method. And so here's kind of two separate ways to solve the same problem. And of course, they have to lead to the same result. All right. Good. Any questions about this example? All right. So last time we were talking about using capacitors to store energy or charge. So we had this idea of, maybe we collect power like using solar panels. And so sometimes it's hot and sunny and we can produce a lot of energy. Sometimes it's cloudy and cold and we're not producing much energy at all. And so we'd like to take the energy that we store during the bright, hot days and use it when it's cold and cloudy. So what we should do then is we should be able to calculate how much energy we can actually store using a capacitor. All right, so we're going to talk about energy stored in a charged capacitor. And so we'll use a lot of the kind of techniques that we developed over the past couple of weeks. So let's start with a capacitor charged to, let's say, plus minus Q. Okay, and so we can draw that. So what we'll do is we'll put some positive charge over here. We'll call this plus Q. In fact, what I'm going to do is I'm going to move my other plate a little bit further away so that we can think about what's happening inside. Okay, and so this one is charged to minus Q. All right. Well, what we know is that we're going to have this electric field between the two plates. And so we know that E is equal to sigma over epsilon naught between our plates. And sigma is just the charge per unit area. And so we said we're going to put charge Q on our plate. So this is Q over epsilon naught A. Okay. We also know that delta V, so we also know that the voltage difference between our plates is going to be equal to E times L. Let's use L for the separation distance. So this is distance L. So it's E times L, but we have an expression for E. It's Q epsilon naught, Q divided by epsilon naught A. And so this is going to be, we'll take this and put it in for E. And so we get Q L over epsilon naught A. All right, so that's the situation we have. What we're going to do is we're going to try to figure out how much energy does it cost us to reach this state. So we imagine you start with uncharged plates, and then you take a little bit of charge, say dq, and you move it from one plate to the other. So if dq is positive, then if I remove that dq from one plate, that plate becomes negative. It has a negative charge of minus dq. And then I take that dq and I put it on the other plate, and so the opposite plate gets charged to plus dq. And what we're going to want to know is how much energy does that cost us? And then we take another little charge dq and move it across, and how much energy does that cost? And we keep doing that over and over. We keep moving these little bits of charge one by one across these plates and keep track of how much energy it costs us. Intuitively, what you could imagine is when the plates are uncharged, there is no electric field between them. And so I move the charge across. That's actually not going to cost me any energy at all. But once I've moved that little bit of charge, now I have an electric field between the plates. So the next time I move another chunk of charge, it has to travel through that electric field, and you have to do work to do that. And the work you do is how much energy it costs. And each time you move a little bit more charge, the electric field gets bigger and bigger and bigger. And so the amount of work you have to do gets bigger and bigger and bigger. And so it costs more and more energy. Okay, so that's kind of the idea behind this calculation that we're going to do. Okay, so let me draw this picture a little bit bigger. I'll keep this expression up here. So let's make our plates over here, and we'll have some plus Q on this side. We'll have our minus Q on this side. We're going to have an electric field that points something like this. And then we're going to take a small little piece of charge. We'll call it dq. And we're going to move it from the negative plate to the positive plate. So let's consider moving a small positive charge dq from the negative plate to the positive plate through the electric field E. Or alternatively, rather than thinking of the electric field, which is a vector, and so we have to worry about doing dot products and so on, we could do just the energy analysis we want. So we also move this charge through a potential difference. Potential difference V. And so we've calculated that potential difference already. Okay, well, the energy cost is du is equal to dq. Remember the relationship between potential energy and potential electric potential was U was equal to Q times V. So what I'm going to imagine is I move a small piece of charge dq, some infinitesimal little tiny chunk of charge, and that's going to result in an infinitesimal little tiny change in energy du, and that's going to be equal to dq times this delta V. Okay, so delta V. All right, but that's just delta V was QL divided by epsilon naught A. So it's QL divided by epsilon naught A. And then we have our dq. A bunch of this stuff is our constants. So here, we're not thinking of changing like the distance between our plates. So we're going to keep that fixed. So this distance L is a constant. We're not changing the size of our plates. So the area is a constant and epsilon naught is a constant. So I'm just going to write this du as a bunch of constants times this q dq. Okay. Now, if I want to know what is the total amount of energy required to charge these plates, well, what we would do is we would calculate all of these du's for all of the different movements of this charge from one plate to the other, and then just sum them all up. Okay, so the total energy required to charge the capacitor is the sum of all, sum of all the DUs starting from an uncharged capacitor and ending with the fully charged capacitor. Okay. Let's say the final charge is capital Q. Okay, so we're going to start from 0 and we're going to move the dq until we reach a final charge of capital Q. All right, so U is going to be the sum of all the little du's, which is going to be the sum of, well, the du's was L over epsilon naught A, some constants, and then we had Q, dq. And what we have to do is we have to do this from an initial charge of 0, sorry, 1 second, to a final charge of capital Q. Yeah, go ahead.
Is dq, is that a distance times Q, or is that a derivative?
Oh, so that's a differential. I'm just using it to represent like a tiny amount of charge. So yeah, that's right. Yeah, d is not a distance. dq is a tiny little element of charge. So this is a small charge. So if you want to think of it, the smallest charge that we could move is, say, an electron. And so maybe we move 1 electron at a time, something like that. Okay, good. The constants, the sum is a sum over Q, right? Q is the thing that's changing. The constants don't have any effect on the sum other than just being an overall multiplication factor. And so we can factor our constants outside the sum. And so we would have this energy that we're trying to calculate will be a bunch of constants times the sum from Q initial of 0 to Q final of, say, capital Q, and then we just have Q dq. All right. So some of you might already recognize what we're going to do. We're going to take the limit that this dq goes to 0. The reason we take the limit that this dq goes to 0 is because this is an approximate calculation, because if I move little chunks of charge 1 by 1, then the electric field changes in like little steps. But that's not really what happens. Like the electric field smoothly increases, and the discreteness of our steps gets smaller and smaller and smaller as we shrink dq down to smaller and smaller little pieces of charge. And in the limit that dq goes to 0, our approximation becomes exact. So if we take the limit that dq goes to 0, the sum becomes an integral. And it becomes an easy one, which is nice. So U is going to be these constants times the integral from Q initial of 0 to Q final of capital Q of Q dq. What's the integral of Q dq? 1/2. That's right. So it's just like the integral of x dx becomes x squared over 2. So we get q squared over 2. We're using q instead of x, but nothing else really changes. And so this is going to be equal to L epsilon naught A. And then we get q squared over 2. And then we have to evaluate it between the two limits. And so our limits are 0 and capital Q. So this would be our constants. Whoops. Epsilon naught over A. We'll pick up our 1/2. And then we get just capital Q squared for our upper limit minus 0 squared for our lower limit. Of course, we don't care about the 0 squared, that's just 0. And so our energy becomes, let's see, it's going to be 1/2 of LQ squared over epsilon naught A. All right, so all we're going to do is we're going to try to rewrite this in a more convenient way. This is the correct final answer. We can just express it in a nicer way. So recall that for our parallel plate capacitor, we had C was equal to, what was it? It was epsilon naught A divided by L, the distance between the plates. And so we have all of those factors here. We have epsilon naught A in the denominator and L in the numerator. So all of this is equal to 1 over C. So therefore, U is equal to, let's see, it's Q squared over 2C. And so this is the energy stored by a capacitor with its plates charged to plus minus capital Q. So the energy stored by a capacitor charge to plus minus capital Q. All right, we could, we have a few other ways that we could, well, maybe 2 other ways that we could write this. One of them is to, let's substitute C for Q over delta V. All right. So if we do that, U is going to be Q squared over 2. And then instead of C, we could write Q over delta V. And what happens? We can cancel one factor of Q. The delta V comes up into the numerator. And so this is equal to 1/2 Q delta V. So this is another equivalent expression for the energy stored. You can see the first one involves Q and C. The second one involves Q and delta V, so no C. We could do this in a third way where we have an expression that involves, let's see, not Q. So we could have an expression involving C and delta V. And so let's see how we could do that. So let's now express Q is equal to C delta V. Okay, and all we're going to do is we're going to substitute this in for the Q here. So, do you guys have a question over there? Do you have a question? Yeah. Yeah. Okay. Sorry. Okay, so if we do that, then what we're going to end up with is U is equal to 1/2. Let's see, the Q becomes C delta V. So we'll get a C, and then we have delta V times delta V. And so we get delta V squared. And so these are all equivalent ways of expressing the energy stored by our capacitor, and which one you use just depends on what kind of information you have available. So if your problem gives you information about C and delta V, you'd use this last one. If you're given information about Q and C, then you'd use the relevant expression. So 3 equivalent ways of expressing the energy stored by a capacitor is the following. So the first one we had, let's look at it, was Q squared over 2C. So it's Q squared over 2C. The second one was 1/2 Q delta V. And this last one was 1/2 C delta V squared. All right. Perfect. Any questions about this? Yeah.
Are we gonna get all of these on the formula sheet, or should we know how to derive them from one another?
Yeah, I mean, I will. So you've already seen the formula sheet that you will have for the midterm that's already available. I will show you the formula sheet that you'll have for the final exam, you know, well ahead of the final exam. And so these will be on there. Yeah. Yeah.
What would be the advantage of using capacitors instead of regular batteries in the context of the solar system?
Sorry, the advantage of using a capacitor over what?
Battery system.
A battery. So yeah, so what you're gonna do is, so you're thinking of using your solar panels to charge your batteries? Yeah, so probably the advantage is that what you probably have to do is you probably have to regulate the rate that the batteries are charged. And so my guess is, like, I've never designed a solar system, so I'm just making things up. But you're probably going to have some circuitry that's going to be optimized for charging your batteries at the appropriate rate, given how much energy is coming in. And my guess is that capacitors will be part of that circuit. Yeah. Yeah. Okay, good. So we have only a few minutes left. And so maybe what I'll do is I'll just talk briefly about what you're going to do in lab number 4 when we come back. So after we finish capacitors, which we're almost done, we have to do capacitors in series and parallel. But once we do that, capacitor topic will be done. We're going to start talking about circuits in general. So we'll talk about using batteries and resistors and capacitors to make different kinds of circuits. Lab 4 is going to be all about trying to set up an analogous system that's easier to think about. And it's going to be a water circuit. And so we're going to have a vessel of water, and we're going to flow that water through a narrow tube, and we're going to measure things like the rate of the water flow. And that's exactly analogous to the types of things that we'll talk about when we have batteries connected to wires. So in the water circuit, we have this water vessel, it's filled, and there's some pressure in that water. That pressure difference drives the flow of water through some tube, okay? In our electrical analog, what we're going to have is voltage differences or batteries that drive the flow of charge. And one of the things that we're going to be interested in is how does the flow change as we change either the diameter of our tube in the water circuit or the diameter of our wire in the electrical circuit. And so the reason we're doing this analogy is because the water circuit's kind of easy to imagine. Do you think you'll get a higher flow rate through a fat tube or a narrow tube? obviously the fat tube, right? If you have a constant pressure difference and you're flowing water through a pipe, like whatever, the pipe that goes to the toilet in your home, right? If you have a fat pipe, you can flow water more quickly than you can through a narrow pipe for the same pressure difference. So the same thing happens in electrical circuits. If I have a battery that provides a constant voltage and I connect it across a wire, you'll get a larger current or a larger flow rate of charge through a fat wire than you will through a thin wire. And so those are the sorts of things that we're going to start to think about. Then, so that will be kind of lab number 4. We'll continue the water analogy in lab number 5, where we're going to try to imagine how do we charge a capacitor with a water circuit. And so we'll have a pressure difference that represents our battery. We'll have a narrow tube that represents like our resistor. And then we'll have a fat tube, which is going to be our capacitor. We've just been talking about how capacitors are used to store charge. So the analogy in water is instead of little bits of charge, we have a volume of water that's flowing. And so we can store a volume of water in a tube. And so we have pressure difference and a resistor connected to a tube, which is our capacitor. And so how do we charge up that capacitor? What are the dynamics involved? How fast does it charge? Those sorts of things. What's the shape of the stored charge or the stored volume as a function of time? And so those are the sorts of things we're going to investigate over labs 4 and 5 when we come back from the break. And so with that, that's where I'll stop. Enjoy your week. And we'll see you Monday. I don't know what the date will be, but after the 26. All right. Oh, yes, because our midterm is 28. Hey, just have